Welcome back to Roid Rage, and this is episode 11. We are going to talk mission design today. We have our own Demyan here to talk. So before we jump into what mission design is, Demyan, can you introduce yourself? Tell people who you are, how you came to be at AstroForge, and why you like mission design.
I'm Demyan Lantuk. I came to AstroForge because where else do you get to try to mine asteroids? Short answer. My background is all in spacecraft. I have a PhD in orbital mechanics and spent a lot of my time optimizing trajectories and building tools that optimize trajectories. First in kind of government adjacent things, then in the startup world. Have stuck with startups and kind of moved to the craziest, coolest thing I could find, which is can we get a spacecraft to an asteroid? You could say NASA's also doing that, and I could work there, but I don't have the patience for like a 10 to 20 year mission cycle. So that because of that, I had to find other crazy people who are the same vein.
Nice. So how did you get interested in this? Like the story I tell myself is that young.
Hold on, where's our intros? We don't get any intros.
Yeah,
we
get
jack shit.
Right?
Like, well, yeah, Debbie gets us all nice. Like, oh, hey, Debbie, we care a lot about
hey,
you.
We're in the room too.
Nice. Sorry. The people with hurt feelings, the one to my left is Matt. The other one to my right is Robin. They've been here since day one.
Yeah.
Welcome back to the
We're
show.
a little sensitive, man. We put a lot of work into
I
this.
want better intros in the future.
I'm sorry. I will work to make sure that everybody feels important in this podcast.
What about Rachel?
Hi, Rachel. Rachel is the real hero in
Rachel's
this room.
not important. Let's go. Demyan, continue on.
She
all right, we've got the
doing
proper
Lord's work
intro
back
here.
there. Yeah, awesome. Orbital mechanics, mission design. I'm going to tell myself that young Demyan picked up a book, picked up SMAD, and said, "Hey, this is what I want to do." Like, why this?
It's not quite like that. When I first went to college, I was like, I need a job. So let me find something that I think I could be reasonably good at and that will give me a job. And I went to an engineering school and
What school did you go to?
I started at Georgia Tech. And I was like, well, they have a good aerospace program and I'm less likely to get bored in aerospace than in some other kind of engineering.
Okay.
So I thought, that was literally the thought process that went into this. And I originally thought I was going to do helicopters, and then ended up doing a course in orbital mechanics. I really liked it, and then thought maybe I could do grad school with the same professor who taught that, Ryan Russell.
Okay.
And he's really good at what he does. And so then I was kind of starting to learn that. I enjoyed grad school more than undergrad. Stuck around, went to UT Austin for even more grad school. So it kind of went deeper and deeper down the rabbit hole. But it wasn't what I intended to do at the start. But once I started down that path, the trajectory continued.
I can't believe you didn't say you went deeper and deeper down the gravity well. Totally missed opportunity there. Yeah.
Why did you make the decision to, I'm assuming you got your master's degree at Georgia and then went to Texas?
Yeah.
Why did you choose to get a master's degree first? It's not a very common path.
Yeah. So actually I knew I was going to do the master's degree first, and then if I could get funding to the PhD, I'd do the PhD. That was kind of my thing. I was doing the teaching assistant research assistantship stuff as that master's, and I realized doing many more years of that was going to drive me insane. So I was like, if I don't have a grant, I can't do a PhD. So that was kind of why I didn't think I wanted a PhD at first. That master's was like enough to get me into specialized work. And I didn't need a PhD, but I enjoyed the master's enough and I got the grant enough that I was like, all right, let's go for it.
And what was your PhD thesis on?
Methods for getting to small bodies and like asteroids and moons using a lot of gravity assists. So I built a tool that actually gets used at APL. I don't know if they actually advertise that, so now we know that they built a tool.
A lot of things come out in this podcast.
Yeah. That APL uses for preliminary mission design of multiple gravity assist trajectories. So if you need to fly by a bunch of planets or moons on the way to something, the tool helps do that. So that was the main focus of my dissertation, and then also did a fair bit of looking for orbits around asteroids. The advisor JPL, Steve Brochart, and I thought we found a novel class of orbits for like a few days, and it was awesome. And then we realized we weren't the first.
What is a novel class of orbits?
So like when you get to more complex dynamics where there's lots of forces at play, you're looking for what's stable or what's semi-stable. Basically, like where can you sit around for a while without floating off?
Okay.
And in this case, we're looking at solar radiation pressure plus a weirdly shaped asteroid. And when you combine those, there's certain places where you can be stable, which are not intuitive. We found them like numerically, literally by like searching a grid. And it turned out we weren't the first to find them, sadly.
So no orbits are being named after you.
That's correct. Not yet.
Not yet. Not yet is the operative word there. Yeah.
Well, we could name like a crater on one of the asteroids or something after him if he gets us there.
It feels like a downgrade. Like
I want the crater where our hardware lands, no matter what velocity it lands at.
All right, fair. Yeah. Okay. I'm mostly excited for this because we get to continue our Tom Cruise versus Tom Hanks debate because we had con ops last time and now we have mission design, which I don't have to draw that bridge. But start off, what is mission design? Like define it for a layperson.
Yeah. So mission design, you have an objective for a mission. Usually the mission designer is you're given an objective or decide like, okay, we have to get to an asteroid or something like that. And then mission design is the when, how, what will it take in kind of physics world to get something there, and then trying to make that fit a spacecraft limitation. So you basically have two kinds of, you have a set of objectives. This is what we want to do. And so those lead to the spacecraft has to be at this place at this time, right? And then you have something like a spacecraft limitation, like we can't use more than this much propellant, we can't be heavier than this amount. So trying to combine all of those and find, in this world, it's mostly the trajectory part of that. Mission design can also include other things, but we're mostly focused on the trajectory part of that. How do we get where we're going at the right time? How do we land on the asteroid instead of smash into it at 3 kilometers per second?
Unless you want to smash into it.
Unless you want to smash into it, yes.
Do we want to?
No. I think this comes down to the point
to be negotiated.
We talk about mission design and crafting how we think of the missions. We can look at some.
Oh, by the way, this is where Matt explains it to you. He's going to sound really smart. Okay, go ahead.
It works
Matt.
great. It works great. This is where you go off on
the listeners will have to vote on explanations.
Oh no,
I'm gonna lose.
Oh, no voting.
No pressure, Matt.
Look at Apollo 11, like as just a corollary that everybody's heard, right? We wanted to go to the moon, land on it, take off, go back into lunar orbit, and come back to Earth. And so you have to plan out the fuel load, how much capacity you need, what the mass is, blah 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 blah, to get there and return home safely.
You know that blah 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 is the hard part.
That's the hard part,
okay,
for sure.
saying,
but it's very constrained in a typical NASA mission, and you see this with like the Psyche mission. Its mission is to get to orbits the asteroid Psyche 16 or Juno to go to Jupiter or whatever. All of these ones have a discrete end. I think what you may notice what Demyan just said is that the challenge we have is there's not actually a discrete end. We don't have a target asteroid that we are going to, right? We have a target envelope that we are building a spacecraft for to fit the targets into. How does that change how you think about mission design?
I think you can't really think about one trajectory, right? It's a whole box that you kind of live inside. And so one of the things that we do that you rarely do in like an Earth orbiter is first say like, where can the spacecraft operate, right? And that's like a design envelope. It's really in the aircraft world, it's kind of equivalent to like a flight envelope for an aircraft, right? So you're designed to operate in this range, and for us, it's a range from the sun, range from Earth, effectively. So we have to think about the spacecraft kind of in a different terms than most people do. And then we have to think about where we're going in different terms because it's not one object; it's one of 40-ish thousand objects, but once you start layering all the constraints on top of that, you don't end up with 40,000. You end up with a small number, and you want to pick the best one, the most metallic one of those, ideally. So it ends up being, you kind of think about it in a different way. Think about it in terms of like Matt said, as a bounding box, as a kind of an area, rather than thinking about it as like one trajectory.
And what are the constraints from the spacecraft side as you think about like how you bound that box?
Yeah. So like I mentioned, in operational space, how far we get from Earth, we need to be able to talk to Earth. It's kind of an important thing. We can get the best pictures in the world. We can't get them back to Earth. The aliens can enjoy them for us. But So we have to be able to talk to Earth. We have to be able to command the spacecraft. So that's one. We can't get too close to the sun, or else we fry. If we go too far, get too cold, we run out of power. So we have to be. So those are ones. We also have things implicit in the spacecraft, like we can't be heavier than a certain amount. We can't realistically carry more than a certain amount of propellant, right? So we can only have so much fuel on board. So there's other outside of that box. There's other constraints that just you can't build a realistic vehicle that does certain things. We unfortunately have to build the thing, and so that means it has to be realistic.
There's one other one that you didn't mention that actually I think is pretty constraining for us, which is the overarching spacecraft mission duration, right? Because you were talking about your PhD and going to multiple bodies or multiple gravity wells and swinging around, and like, yeah, we don't let you do any of that fun stuff. We're like, no, get there as fast as you can.
Yeah, there's real value in simplicity here, both speed and simplicity, and a lot of that is just we want to iterate quickly. So there's definitely a lot of things a lot of tools or like techniques out there that exist for getting, let's say, cheaper trajectories that we don't use precisely because we really want to get there fast.
Are there Terraform trajectories now?
Don't mention it. I don't want it to be put on.
All right.
Yeah.
What are, I guess, just so everybody understands, like the bounding box that we're playing in right now, what do you see those limitations to be on mission design? What are the hardest ones for you to go? And like, what are your physical limitations? So Robin mentioned 2-year lifespan. We want to be under in every case. What else do we have?
Yeah. So we right now we're designed to 5 kilometers per second of delta V, which basically means in an ideal world, you could change the speed of the spacecraft by 5 kilometers per second, which is a lot. It's a whole lot. But in the domain we're looking at,
how much is like a let's pick like a low Earth orbit satellite, Starlink, right? Like how much delta V do you think like a Starlink has, like as a comparison?
Oh, they probably have about 100 meters per second on board. That's
Okay.
probably about.
Wow. Okay.
That's yeah. That's and there are other like a large spacecraft going to geosynchronous orbit.
Yeah,
Has to circularize itself, might carry, let's say, like a big commercial bird might carry up to 2 kilometers per second. That's that's a big fuel load.
And to use like normal terms that we understand, it's about 11,000 miles per hour difference. So imagine your car going from 0 to 11,000 miles per hour. Like it's not a small amount of change.
Wait a minute. Terms that we understand. Where's our audience based out of? I'm pretty sure that they're going to understand.
Our audience is based out of what is it, Kenya?
Kenya.
I
think they're on the metric
We're
system.
harder than that.
I think we're number 3 in Kenya. So
we have a few listeners in England
I'm just saying.
and Germany
I'm
too,
just saying.
so-
Don't
okay.
you know? Don't
So
be a
kilometers
metric
per
hater.
hour or miles
This is
per hour.
America, Robin. I use freedom units, miles per hour. 11,000 miles per hour.
I'm going to put a tariff on your speech.
Yeah, okay, I just have a bucket in the middle.
Yeah. Instead of you're
I
late
think
for a
we- I
meeting,
think
you
we'd all
used
run out of money
English
really
units.
quickly.
Oh,
What constraints clash the most for you?
So there's a class, in classic kind of mission design, trajectory design, you usually trade propellant for time. So the faster you want to go, the more it's going to cost you fuel wise. So that's kind of the usual. That's a common. It's kind of common simplification of if you want to save fuel, you just take longer. But I think the one that's maybe the most constrained for us is actually the one kind of Robin alluded to is also simplicity. Like for Odin, we limit ourselves to 1 flyby of the moon. We could have gotten a lot more, let's say, efficient trajectories by doing 2 flybys of the moon, but it's just more complicated to do operationally. So you say, okay, well, maybe I can get this slightly better, cheaper, faster trajectory in some way, but if it's really complex to implement, is it really better? So I don't know. That's I think common
maybe a
trade-offs.
future mission will let you do that.
Yeah, well, you might have no choice.
What do you mean you might not have a choice?
Well, we don't pick our launch injection, right? So we don't pick where the rocket drops us off because that whole being a rideshare thing, which is a whole which makes our mission design unique in a different way.
Yep.
But because of that, we can't necessarily go wherever we want. We have to take wherever they are happy to drop us off and go from there to where we need to go. And so right now for Odin, we could always do that without a second flyby of the moon. We can't guarantee that for Vestry because of the low thrust electric propulsion system.
I think I need to book a meeting with you a little bit later. I feel like there's some bad news coming that I just got a preview of. That I'm.
It really does. Like, this is a slow roll for like, hey, Robin, the mission's
Robin,
going to
by the-
change
by the way.
significantly.
By the way,
There's a new
Can you-
spacecraft mode.
Can you talk? I think that's actually important. Can you talk about, as we are moving to electric propulsion, like that's a different constraint? How do you think about that as a how many orbits we have to do in the moon, and then like how that thinks about your orbital trajectories out to which asteroids?
So I think it's like it's start off, it's a fundamentally different class of trajectory design problems. If you assume high light, you can have basically like a lot of thrust, you can change your trajectory quickly, or you can't. I'll give a really great example for, even though we have all this delta V on board, so you dropped off, we have 4 days to get to the moon. With Odin, with even a lot less delta V, we could have, let's say, diverted to the other side of the moon if we needed to, and it would have cost, a couple hundred meters per second, let's say delta V. With Vestry, even at the highest power mode, we get at best 25 meters per second per day of firing time.
Okay.
So we can't, even though we have all this fuel on board, since we're at the moon in 4.5 days, right? We're only able to move by 100 meters per, 125 meters per second total in that time anyway. So even though all this propellant is on board, you have to kind of slow play it. You have to slow play. And so there's certain things you can't do that you could do if you had more basically more thrust. So it's just it's kind of a different way of thinking about the design problem, and it limits you in certain ways, gives you the ability to have a lot more delta V. Somebody want to ask, why would you do that to yourself?
Yep.
So we're thinking about something like 60 kilograms of propellant for Vestry. If you wanted a high thrust, an efficient, like nice high thrust system that did that, the same delta V would take about 10 times more propellant. That's usually the rule of thumb. So 600 kilograms which is a lot more than the mass of the whole spacecraft. So that's why it's like, well, if you want that delta V in high thrust, you're going to pay for it in propellant.
And you said a lot of this depends on where we get dropped off. Do you have a range of where we get dropped off before this? Like, how do you calculate for this, what feels like a known unknown?
Yeah, well, we know that we're riding with intuitive machines, and so they're going to the moon.
Okay.
So we can pick a date and plot a trajectory that separates where we expect them to separate near the Earth and then go to the moon. And we can compute kind of that approximate trajectory. And that gets us close. And for now, eventually they'll give us coordinates, basically where as they work with SpaceX to figure out where the rocket's going to take them, they're going to have more and more knowledge of where they can get dropped off, and they'll pass that along to us. But until then, we kind of have to guess. And what that means is we have to build a system that's robust to changes in the launch date, that's robust to changes in those injection coordinates. Because we can't control them, we have to make sure that we can accommodate a wide variety.
It's also what I think this is a very different mission profile than any other company's ever done, because we don't get to pick. Like, this is the challenge of rideshare. We don't control when the rocket launches, which means we're responsible for planning trajectories on every possible day and every possible time we think the rocket can launch, which without modern compute, this problem could not be solved. Like, if you look at how JPL calculates trajectories or has in the past, like, this is not a 24-hour process. It's a very long process of calculating a trajectory. Usually it's done 10 years before a mission, whatever, right? That they go through and update as it goes through. We have to calculate essentially thousands of trajectories on a very quick timescale and be able to change them to be able to handle this rideshare model. So it's just a totally different way to think about planning it. Probably not super hard for an impulse burn or a very quick burn that we can calculate. This is a big challenge for a continuous burn, because now you're not just doing one calculation and propagating forward. And if you think about it in a physics model, it's a spaceship that doesn't have any other real forces on it as it goes out and transfers. Now we have a continuous force for 3 months. That's a lot more computation to calculate. So it's going to be a challenge to us, and I think it's going to be an AWS bill that I don't want to look at, but it's kind of what's required to do.
Yeah, I've been meaning to talk to you about the bill. Josh, anyway, we've been doing some compute lately.
Yeah. Somebody asked me to figure out which targets are reachable given some kind of constraints. I don't know who asked for that, but somebody asked for that.
I actually know what that costs in real dollars now, because I got the compute bill.
Do you have any more requests?
We're good. Yeah. We're gonna extrapolate from the data I got. Yeah, no, it is a very different thing, Matt, right? Like I'm a liquid propulsion guy, right? So all the design work that I've done, you end up doing like what's the impact, what's the partial on delta V or payload compared to whatever design trades you want to talk about, whether it's distance or how big the spacecraft is, all that kind of stuff. And that's not really our trade space. Our trade space is what's the partial of number of targets that I can actually get to on any given launch day, right? So like I want to launch on Tuesday. Can I get to 1, 3, 60? Okay, now do that same math for Wednesday and then Thursday and then every other day of the year and potential launch day. And then if that number is ever, let's say 0, we have a real problem because we have to
guaranteed they'll launch on that date.
Yeah, of course. and I guarantee that'll also be on a holiday, right? It's always people laugh at me. That's why I do always do my schedule estimates and increments of holidays. Anyway, doesn't matter. So it's a really interesting way to look at it. And actually, Demyan, I got to give you and your team a lot of credit because you've come up with a way to visualize this really complicated problem, multivariable problem, in a way that I can actually communicate to other engineers on exactly like, nope, spacecraft has to get bigger or has to get smaller or lighter or we need more propellant or whatever the case may be. And that's actually a pretty tough order. Like, I don't know how many people have looked at a pork chop plot. That's already complicated. Now I need to do one for all kind. I have to have a stack of it, like a movie.
Basically.
For every single one of these constraints, a weight chart, a delta V chart, a communication chart, and it just becomes it is a very difficult problem that we have to solve.
We should, like,
what
it's
makes
a good
it
thing we
fun.
have computers.
Right?
Yeah. And it would be, I think, kind of point, it's easier to solve if we weren't, flying in less than a year and, had a lot more money in the bank. But really the part is that we have to make real decisions about,
Oh, yeah.
well, sorry, you can't do that.
Spherical cow problem, right?
Yeah, exactly.
Well, I mean, just to draw an analogy here to Psyche, right? Psyche, obviously, mission out to Psyche 16. Psyche was famously delayed by a year. And so they recalculated the trajectory. And in our case, like, we would have never been able to hit it. Psyche actually had to take on a totally different mission profile. It took much longer to get there.
I think they had to drop their ride share.
Yeah, they had to drop.
Ooh,
they
no,
dropped off
don't say that.
2 other satellites that are still sitting in some closet somewhere that NASA claims they're going to sell to people.
Wait, do they have good instrumentation?
Yes. Are they going to give it to us? No. And if NASA's listening, which probably isn't happening.
I'm going to keep asking, but stop giving my phone number out.
Oh yeah, we should put Robin's phone number. We should just make that the title.
Yeah.
So he can't block it out.
We should make it easier. Make it easy for the AI to scrape.
Yeah.
Just put it in text.
Oh man.
But that mission had this thing. They couldn't change the target, right? The mission was built to go to Psyche. It's the fucking name of the mission, and so like you can't change it a year later to go somewhere else. Ours is not, and that's kind of the beauty of what we have is like if we have to delay a month because of rideshare or 3 months or 6 months or whatever that time is, we actually just simply pick a different target.
Wait a minute. They get a cool name like Psyche and we get like 2022 OB5.
We're not going to 2022 OB5 anymore. We've discarded that asteroid.
Oh.
Yep.
Well, you know what I mean.
In the trash now. Discard it.
Well, the first one we get to is going to be named Matt. I've already talked to the asteroid body, the IAAC.
You just want an asteroid out there just saying, just
Matt. Yep,
It's
just
probably
Matt.
not taken yet, so it's probably
There's a Helen Keller. Why can't there be a Matt?
So many reasons. Yeah. Like, that's a whole nother podcast. Did you have a script?
I mean, we start with a script. We start with really good intentions, and then somewhere, Rachel, we're like 22 minutes into it, and like it just sort of like
it's like the whole mission design problem. You start with a good idea of what you want to do, and then you end up somewhere else.
But generally, we find our way back to a good path, like more often than not.
You're the director.
Next
There's
question.
no directing. I am curious, like, we launched Odin. You spent a bunch of time creating trajectories for Odin. How much of that work, either from just sort of like a process perspective or an output perspective, is transferable to Vestry? Is this a clean slate? You're just starting over again, or like are there learnings that you can carry forward that are actually helpful to you and your team?
Yeah, the trajectory itself is actually very different, other than the beginning part.
Yep.
So everything else with the trajectory itself is very different. One of the things that was really good about the Odin thing, and because we have to accommodate all these launch slips and changes and unknowns, there's a lot of emphasis placed on just the process of generating a trajectory, right? Like, so by the end, we could get a new target, like, hey, this new target appeared, and within a day, we could have a flyable reference trajectory for Odin, like, which is pretty incredibly fast for that whole thing. I don't know if we'll get it down to a day for Vestry because electric propulsion is a little tougher.
We will.
But yeah, cloud bills.
Depends on how much we want to pay
But
Bezos.
so that part of it, that idea of having a pipeline method and a sequential process, very much carries over. A lot of the tool set carries over.
Okay.
The trajectory itself is very different. There's a lot of new tooling, a lot of stuff that has to get spun up, that is getting spun up. So I would say the way we think about the problem, I think we refined the way we think about mission design with Odin in a way that's very applicable. A lot of the specifics of the tools that we have to use are different because the problem itself is different. The trajectory is different.
Can you talk about some of those tools?
Yeah. So so basically, there's early on for like preliminary mission design, we have a generated database using right now just obviously a Lambert solution, 2-body problem, big kind of pork chop plot style.
Obviously, a
database.
Lambert solution. What is a Lambert solution?
Obviously.
I was gonna let that roll and then be like, hold on.
By the way,
There was a 3-body problem joke somewhere in there, but like we should just stop
Can you
it.
walk us through what a Lambert solution is?
Yeah, absolutely. So Lambert solution, if you're under the gravity of one thing, like let's say that you're on the Earth, you're at one position and you want to go to somewhere else. So you just have position A, position B, and then to go from position A to position B in any given time. Let's say you have 1 hour versus 2 hours or 3 hours. There's one direct arc to get you there. So just technically 2. We don't have to get into that. That's the Lambert solution. But yeah, there's so if you have to go from point A to point B in 1 hour, right? That's one arc. That's one path. And what that tells you is what.
Tell my wife that. You know how many Starbucks bills I have on this? Like one, I had to go pick up the kids from school.
You have more than one gravitational body.
Is that what it is?
Life.
So there's no Lambert solution.
There's no
Yeah,
Lambert solution.
that's not a simple 2-body problem.
Yeah. That's unfortunately, I think the math for that gets very complex.
Okay, continue on. So we got a Lambert solution.
Yeah. So we can do a bunch. They're very fast to compute and
Like a Lamborghini.
Like a Lamborghini, exactly.
Almost like a Lamborghini solution.
But
what is fast to compute? Give me a relative scale.
Oh, so you can compute about 1 million in a second.
Okay.
But we don't bother recomputing.
Wait a minute. Why is my bill so high? Are you Bitcoin mining?
The problem becomes
Oh.
that you don't, sometimes you don't know, because you don't know what the answer is going to be. Let's say you say, I want this velocity. Well, you have to compute a bunch until you find the right velocity. So we end up pre-computing them and storing them so that we can search the solutions, the stored solutions on other things besides the positions and the time. So we can mostly velocity delta V. Hence why all those queries for, hey, give me all the thousands of solutions that match this criteria, the cloud gets to get their pound of flesh for that. So so we compute it that way, we store it. One of the reasons why we have our own database for this is at some point we want the equivalent for electrical propulsion. We're still building out the tool chain to do that. And then that will be a lot harder to compute, but once it's stored, and we'll query it. We'll look for it the same way. So we'll just say, give me the low thrust trajectory to this asteroid, and we'll have it stored. We're getting there, working on that one. That's part of why the system was built from the ground up to be scalable and extensible to the next mission. Because some of you who, the like 3 of you who have looked at NASA's small body database will know that there's actually a tool online to do this calculation for you. Yes,
What? I didn't know that this episode was just going to be watched.
Wait a minute. Why did we?
It has some limitations, Robin. Don't worry about
it. No, like, what are those limitations? Like,
you mean like an Android phone has limitations over an iPhone? Like, what's up with this?
Yeah. So yes,
Yeah, we're definitely having a meeting after this.
So I may no longer be at AstroForge after this. Yeah, what was the cloud bill again? But yeah, so there's a tool, but it basically locks you into what they have computed before. So that they actually do it the same way. They have a big table computed, and you can query their table. So whatever is in that table, you can check and say, oh, I want to go to this object. I want to go here, and give me these times, these dates, and it will return a couple solutions. It is limited how many solutions it will return. So in our case, where we want thousands or millions.
Oh yeah, because the compute gets expensive.
Yeah, you wonder why. You wonder why it only gives you a couple at a time.
Their database is running on a Raspberry Pi or something.
Exactly. So it's limited. It also doesn't let you add additional things to filter by, right? So we want to be able to filter by whatever we want, which means we have to write our own queries, which means we can't use their database because similar thing, because arbitrary query would mean we could have them do arbitrary amounts of compute, which for some reason they don't want to do. So that's
All right.
So there is a reason. There's sometimes method in the madness.
Yep. Okay. So this is super easy software to roll. Like
So-
just easy.
I mean, so that you know, this literally drove me. I'm already having meetings on like trading, whether we do it on prem or off prem. Like I literally got the bill and was like, I could buy a data center for this.
Yeah. It's the crazy part is not that much data. It's like a few terabytes of data. So data wise, it's not that much.
The story gets better and better and better.
It's not a small amount of data, but it's
So
not,
wait, are you
it's
just
not
telling us
crazy.
that you guys are really shitty programmers, or I don't understand?
We get it from NASA anyway.
Yeah. Oh, okay.
Yeah. I'm telling you
So what we really need to do is spin up like a lot of users,
Mm,
and then each have them only do a small number of queries, and then aggregate.
that's true.
back.
And then we have a cloud instance for each of those users. Or we do those on prem. Do we have VPNs for each?
No, we'll just get interns.
Okay. Yeah.
It's not a bad idea.
That
Okay,
might be
problem
cheaper than the cloud. Yeah.
Another question for you, because mission 3 is designed to do a rendezvous, which we defined last time, so we don't have to define it again. Does that make your job harder versus a flyby of Odin?
We did mission requirements last time.
We did. Oh, perfect.
That means like I don't listen to this shit.
Well, that's what I saw around. Is like if I don't know the content of what you talk about, the useful content of what you talk about.
It's really,
then
really
there's a
low.
problem.
It's really, really low.
So yeah, that's.
Oh, I'm totally doing that Chat GPT query. Like take the transcripts and be like, please,
summarize this to the most useful
content and get out like the one
How
tweet.
long of a podcast should this be?
Yeah,
22 seconds.
So I'll say in a lot of ways the rendezvous is harder because you have to match the orbit. So from like a physics standpoint, a rendezvous is a lot harder to do. From a trajectory standpoint, it's actually less constrained. So in some ways that can make it easier to calculate trajectories. Say in some ways it's
What do you mean it's less constrained?
So a rendezvous you have to match position and velocity.
Okay.
So because you have to match position and velocity, you know exactly what the end state is. Whereas in a flyby, you know your position, but you could have any velocity at that position, right? So it makes it you approach the problem actually differently in those two cases. And so if you're gonna rendezvous, what you actually do typically so we talked about the Lambert, the low fidelity solution. When you go to full actual high fidelity solutions.
Does that have a cool name too?
No, there's no. So I'm gonna petition to have that named after me. But
this is your moment.
This is my moment right here.
This is the Demyan now.
That's right. Yeah, that's right.
It's like a dance move.
I don't want to see that dance move. So what happens is because you know where you're going to be, you can actually start at the rock, at the asteroid, and go backwards in time, right? And say, I'm going to approach from this direction, so can I just go, compute that backwards in time? You can't do that with a flyby because you don't know what speed you're coming by. You can't do it. So it kind of opens up another tool in the tool belt that you can do with a rendezvous that you can't do with a flyby. So in some ways, you could say that makes it easier. You still have to figure out how to connect that back to Earth and how to connect that to a trajectory that passes by the moon and all that. So it's a different problem. But in some ways, it is harder physically to actually achieve, right? So in terms of actually making the spacecraft do it, it's way harder. But in terms of the mission design, a toss up because you get some new tools.
I don't even know what the right follow-up question is,
Yeah.
but I'm also aware of time. So before we go into the mailbag, which I will say, this is the first mailbag we've had someone call out the guest specifically with a question. So
Nice.
I'm gonna
Didn't come
kudos to
from me, I
Demyan.
promise.
It did not. Well, it might have. I don't know. We'll see. Any last things we should know about mission design that we did not talk about?
I mean, that's very broad.
It is very broad, intentional.
Welcome to the
intentionally broad.
podcast.
Let me ask this question differently. Anything
Yeah.
that is unique about our mission design parameters being rideshare from a standard mission that have really driven you to do a different profile on how to create these paths?
Yeah, and I think, and that kind of maybe is a good way to decide mission design. You think we would have already designed all the missions in space by now after like 50 years of designing space missions, but because what you're doing, what you need actually keeps changing, the process itself keeps changing. That's one of the things that's unique about, like, yeah, we have a whole different problem set that very few people have even attempted to solve because it hasn't just been run into before, right? So that I mentioned already for Odin, where we got the process down to a day. So that really focus on getting the process down, and that process includes not just like a preliminary, like this is a good enough trajectory, but includes, we can tell the ground antennas where to point, right, to get to the spacecraft, and we kind of that
It's
whole
important.
thing it turns out it's important.
Yeah, it turns out.
But yeah, so I think the process is different because we have to focus on being flexible and being adaptable in the future. So a lot of it, when I look at what I'm doing now, it's like, okay, how do I make this process better so that when I inevitably have to do it again, it's a little faster next time. And if you don't have the same mindset, even though you're going to do the process again and again, you typically don't think about it that way, right? You think about it of like, okay, well, I did that part and then move on to the next part of the process. Whereas in our world, because of the rideshare, we're going to be repeating the process over and over again. So we better make it good.
So you're just awesome.
Yeah, in addition to lots of other things.
Yeah, okay.
Yeah. I mean, I think literally the first day I walked in here and I saw a pork chop plot and it was like, that thing hurts my brain, but I'm really glad somebody else gets to work on it. So thank you for doing that. Awesome. All right, let's roll in the mailbag. First one from Levi. Hey guys, big fan of the pod. In the long-term future, do you ever see yourselves reusing your spacecraft, or will you just be working towards making them as cheap and disposable as possible?
No. Like reusability, I don't understand it from a
Didn't we have this
spacecraft
question last time?
perspective.
I'm going to disagree with Matt.
We answered this
Demyan
question.
can disagree, but I'm correct. No, the goal here is to commoditize the spacecraft to make it as cheap as possible. And when you have reusability, you have to have longer lifetime of parts and all these kind of things. You have to be able to handle more radiation. And we've done reusability on spacecraft before. It was called the Space Shuttle. And it ends up being one of the most expensive things ever created. I think when you talk about something that has a very short duration in space, like a Falcon 9, reusability can make a lot of sense. Even to some extent, second stage reusability on a rocket can make a lot of sense. I don't think it makes a lot of sense on a spaceship that is trying to be at a price point of sub $10 million.
Demyan?
Oh, all right. The counterpoint that I think the talking about far future, I think we will see something where it's going to look more like mining and transport on Earth. And I think that's where at some point it's going to make sense to build like something that's the equivalent of a cargo ship, a bulk carrier. And then those things on Earth cost $100 million, right? So I think, quote me on that. I'm pretty sure I'm wrong. It's not that.
Cargo container definitely doesn't cost $100 million.
Not a container, that bulk carrier, not a container.
Oh, the
bulk
ship?
carrier, the ship.
Yeah.
I think the ships like literally cost $1 billion.
Yeah, I was going to say
Like,
actually
I'd
way
be
more.
low, I'd be low on
Yeah,
that.
you're
Okay.
it's way more.
But the point being that
Rachel can check us on that.
at some point, yeah.
I mean, like
I think our
commercial
audience is gonna
aircraft are like $250 million, right? I mean,
yeah.
I mean, not that anybody buys them; they lease them.
Yeah. So, I mean, presumably somebody pays the manufacturer for them.
I mean, it's true. Commercial, I mean, there is a whole tactic here of like, yeah, you can draw the analogy. Commercial aircraft are, if you had to pay a one-way trip on a 737, right? We hear this analogy all the time. They're what, $50 million a piece? Like each plane ticket would have to be $1 million. It's not a reasonable business model to go after, right? So reusability can really drive costs to get lower to a certain point. I think the problem with us at deep space and going for long mission durations is the long mission durations are an extremely long flight time on a 737. And like there is a number of hours where that hole loses its integrity. And we come very close to that. And in order for us to get more integrity, it's an exponential increase in cost today. That doesn't mean in the future we won't invent better computer chips or better radiation tolerances or better propulsion systems that can last longer. Those are not available to us today, and we already have lifetime issues with our propulsion system on just one mission. Attempting to reuse our propulsion system for mission number 2, like it just wouldn't work in today's tech.
It actually wouldn't make sense. Even if we could even if we could refuel Vestry and fly it again, we would be beyond the design life of the thruster. So but I think there's a far future.
Yeah, but you don't take that super cargo container on land, right? Like you've got a super cargo container in the ocean, you got a train on land, then you got some trucks, and then you got a little UPS guy, and then Amazon brings it to my door before I even order it.
That's true. So you got to separate the mission.
Like you could separate the mission out into different phases, so that
we would have to, in order to go back in. We get this all the time. Like, can we bring back material to low Earth orbit?
Yes.
And the answer is, from a physics perspective, like not really.
Well, yeah.
You could do some exotic skip trajectories to try to slow us down. We could do a lot of delta V change to get us back into orbit, but realistically, you kind of can't.
Well, I think you would do something like OSIRIS-REx did this, where they dropped off a landing capsule and then the mothership did a flyby of Earth and continued on. So then you'd have to do something like that. You have to drop off something, and that capsule probably is not reusable.
Yeah, right? The capsule itself is not.
Doesn't make sense.
But there can be a mothership or a transporter that's doing the loop, like a bus route.
Yeah, and we'd probably have to split the transporter from the miner at that point. So this is like far future, right? I
mean, it's no earlier than like next year.
Yeah, exactly. Yeah, far future.
That's what the interns are going to be building on. Next question from Micah. 2 important things to know about Micah. He is from Texas, and he thinks that Tom Hanks beats out pretty boy Scientologist Tom Cruise any day. Those are his words, not mine. How many hours are put into stress analysis before you commit to a design?
Yeah. So I guess, it's been a little bit depends what you mean by like stress analysis. One of the things we do is we do what we call like a Monte Carlo analysis, where you vary the inputs. You say, what if we start a little low? What if we start a little high? What if our engine's a little less underperforms a little bit? Can we still make the mission work, right? What does it cost us? How much more time or fuel to cost? So we do that kind of analysis on a few trajectories to kind of make sure we're in the ballpark of, if we say the thing is going to be like 100 meters per second of delta V or whatever it is, 10 kilograms of propellant. If we are off by a little bit, is it 11 kilograms or 20 kilograms of propellant? We kind of want to know, right? So
yeah, I don't think that's what they're asking at all.
No, what are they?
I think they're just asking how much finite element analysis we do on the structure of the spacecraft.
Apparently a lot, because it's late.
Why did I bring that up?
So the other part of the question was, how do you account for space pirates in your trajectories? But I don't know that we're at that point either.
Well,
Space Force.
Right. Yeah. Right now, we account for it by the fact that we're the first ones out there, and that we can be the pirates.
It is actually. I know we say this jokingly when it comes to space pirates, but there are other countries looking at doing this, predominantly China, and there is always going to be a concern in the back of our mind that when we get to an asteroid, someone else is going to try to go to that same asteroid body, and this is why, even though we announced with Odin what asteroid we were going to, we knew that it was a little bit of a subpar asteroid. We went out to it, and we went out to it because of the launch delay. I'm not sure that's going to be the case for Vestry, and there may be a thing where we become very secretive about where we're going again. So it kind of plays into, like, we do have to, they're not going to be space pirates. They're not going to come in a fucking pirate ship and rob us, right? But like,
know that yet.
There is a real thing that
that was a movie, Ice Pirates.
What?
Yeah, there's a movie, Ice Pirates.
Is it a space pirate?
Why do you say that so confidently, as if that's like a
Ice
major
Pirates?
Ice Pirates.
Anybody else has heard of this movie?
It's pirates in space.
What year was this movie?
Oh, let's not talk about it.
Okay.
All right. Last one from the readers.
Tom Hanks was not in
It
Space
doesn't sound
Pirates.
like
This sounds like a cocaine-induced 80s movie. Let's see.
From Alessio, in recent interviews, Eric Schmidt has said he bought Relativity because he believes the idea of putting large data centers into LEO is a good idea. Since this idea has been floating around for some time.
1984.
Not how long.
Sorry,
this
the
idea has been
movie,
floating around.
not the data centers in space. In 1984, they wanted to put nukes in space.
Alessio would like to know your thoughts on Eric Schmidt buying Relativity and broadly data centers in LEO.
Eric Schmidt buying Relativity, like, congrats to the Relativity team. That company had, raised a lot of capital and was building Terran, which is a pretty massive rocket and a huge financial burden. And I think the leadership there did an amazing job in the early days. And as it came later, like, it was clear that they were not going to be able to raise capital to continue on with the project. So to have Eric come in and kind of save the company, continue on, like, it's huge. I think for everybody I know that works there, it's great that they get to continue on the dream of building Terran and that lives on. Data centers in space is an interesting concept. I'm not sure that. Look, to me, there's some challenges to it. Number one is the most power we've ever put in space, I believe, is 25 kilowatts on the Psyche panels. Juno may have been. I don't know what Juno was. It might have been a little bit bigger, but like
look it up.
notionally, we're around the, let's say, double-digit kilowatts that we need to put in space. That's actually not a hard thing to build on Earth with solar panels. But going higher, what you need to do to run like an actual data center, right? You're going to talk about in the hundreds of megawatts. Like those solar panels become kilometers in size just by doing basic math. And controlling things at that, when you have to account for solar pressure and even some atmosphere that you're getting in LEO, it's actually really hard to balance those. There's modes that happen. There's kind of sine waves that form on this. We even see it on smaller spacecraft. It's a really hard thing to balance. And so I'm actually not sure if it's physically possible to build data centers in space. I think there needs to be a lot more analysis done or some kind of corrective action taken on those large structures in space. There is a physical limitation to structures in space. We study this a lot on ISS. We know about it. I don't know how you get much bigger, at least with current technology. So that's really my challenge to data centers in space. But look, when you have Eric Schmidt by a company, like this isn't something we study every day. Maybe he's figured it out or maybe he's got the solution there. And if nothing else, like great things happen when you try. Maybe they'll figure it out.
I mean, I'd love to know if he needs some rare earth metals.
That's true.
We'll
Maybe
we can deliver to
delivering
him.
to Leo.
Yeah.
Reconsider.
And just reference, Juno had 14 kilowatts in Earth and 400 watts at Jupiter.
Yeah. And
So,
Psyche, I
not
think,
a
was
lot.
25.
400 watts.
Yeah.
Oh man.
I mean, it's far away, right? And Jupiter has a ton of
Thanks, Matt.
radiation.
I appreciate you explaining.
Yeah,
that
sorry.
to me.
Just in case you guys didn't know, it was
Yeah,
a little
Jupiter's
farther
far
away.
away. Thanks,
A
Matt.
little farther away.
Got that one.
Yeah.
Matt's explaining it.
Well, I mean, the other thing is like maybe we could just figure out if it's going to reduce our his computation bills on the cloud. We can get some data centers in space.
Oh, that's
It's
true.
cheaper.
Yeah. If you can give us a nice cheap price on those data centers in space, we can be.
Is it still called cloud computing at that point? Like,
orbital computing?
yeah, orbital
You're
compute.
above the clouds.
Yeah, something, yeah.
Call it?
Yeah. All right.
I don't know. It's a cool concept, but it just, the other thing
I mean, you
is-
could do it on the moon.
You can do whatever you want. I hear the arguments for like thermal. There's huge cooling and data center cooling is a problem. But the reality is, I think data centers replacement cost right now. I mean, you hear what did Jensen say last talk he gave, right? The founder of NVIDIA came out and said like essentially the new chip is going to replace the old one. Like replacement cost on servers seems to be on a timeline of about 2 years. So essentially the question boils down to today is, can you launch a spacecraft that has 5 kilometer wide solar panels, right? That can handle 500 million watts of power or whatever, and then replace it every 2 years and make that profitable.
Yeah.
I don't know the math there.
500 million.
I was going to say, yeah, it doesn't seem intuitively, this is not just intuitive, but just any kind of design things, like all the things that you need, like power and cooling and data, are harder by being in space. So yes, you can get continuous sunlight. That's great. You just need a massive panel.
Make them big enough and you can start getting shade on the Earth, though.
That's
Could cool it off a little bit.
Well, but let's be clear. I mean, in 2004, we all thought there was a whole bunch of hiccups to landing a rocket,
Oh yeah.
right? And like,
I mean, there
don't
were
wanna-
some hiccups.
There was a lot of hiccups. People were like, "Hold on, the fuel doesn't make sense. How do you do this? Can this
It
happen?"
turns
Right?
out
And so,
when you build a new rocket, there are still lots of
like
hiccups.
the greatest things that have happened are when we all sit here and say like, "Here's all the problems with it." Well, that's all cool. What if we get rid of all those problems? Is it a great idea? And we haven't spent enough time, so I never want to shit on these ideas. They can sometimes turn into magical moments. I don't know if it's going to or not.
Yeah, that's right. All right, we're way over time. That's a wrap. Thank you, Demyan, for coming on and telling us about mission design. I guess I'll thank Robin and Matt since they were a little upset that I didn't treat them with the same graciousness as our guest. But
I expect a better intro next podcast, or I would quit.
Oh, okay. Don't tempt me with a good time.
Is that a promise or a threat?
Yeah.
If you enjoyed this, subscribe.
I mean, we can't leave
send us
that
some
alone.
Questions, and thank you all. We'll see you next week.